Okay, this is February 8th, Night Watch Institute. I don't know, sometime at night. There's Parvati up in the sky, and yeah. Ooh. Anyway, we're going to be discussing what would probably happen with light around the proposed craft. So, anyway, just to kind of illustrate the point, and again, I apologize to any engineers or academic superiors out there. I'm self-taught, so if I get any terminology or anything like that wrong, I defer to your corrections. So anyway, you have a smaller mass, a larger mass. If these two, if everything else in their surrounding system is equal, this will pull more towards the second mass than the second mass will pull towards the first mass. More specifically, the centers of each of these masses, right? Both the centers are attracted to each other, and regardless of how far apart they are, they're going to experience this tug, be it inches or astronomical units. So if you were to think about this in terms of a star system, now we can complicate it with a third body, and that is actually one of the underlying premises of the three-body problem, which was a really, really brilliant book. I highly recommend it. Now, I don't necessarily think it's the only way things could go, but it is a very good book. But if we introduce mass 3, right, one of the points that the book makes is that this interaction is no longer nearly as predictable. It becomes incredibly more complex because you now have this mass, which is now also exerting a pull force upon this, exhibiting a pull force upon that, and both of these are exhibiting their own forces in return. So what would end up happening if, say, this was somewhere in between that and that, you would probably have some kind of situation, let me get that, where this would fly kind of in an angle between these two, and it would want to go that way. However, at the same time it begins this trajectory, this is inclined to go more like that. And this, on the other hand, is more inclined to go like that. Now, you can imagine what happens. These are all going to go at different rates, because depending on which of these is set in motion, how fast, and with how many, newtons, its vector, everything else, even upon 2 dimensions, this can get extremely difficult to try and calculate. Now, if you add a third dimension to that, and then the addition of a, half Border Collie, half Great Dane, the system just gets incredibly complicated, to the point where, it influenced one of the really brilliant passages of the three-body problem book. So anyway, the reason I bring this up is because it kind of explains the next part. Now imagine what happens if you have a black hole. Now that we kind of have that little primer on our, most basic understanding of the problems in trying to calculate this kind of stuff. We have, let's say, let's make our black hole actual point of infinity, not quite infinity, but we'll say gravity as it approaches the limits of infinity. All right. However, it's not infinite. It is finite, which means there is a fixed radius around it upon which stuff outside of that system is not going to get sucked in. So if you are past this line, you inevitably get sucked in to the black hole, barring any other outside forces acting on it, or addition of an inside force, or, you know, however you would escape that kind of a situation. If you're outside the line, you eventually escape, unless there is another force acting upon you. This line, this kind of imaginary spherical radius around it is probably going to be very, very, very much like the seashore, in that it isn't going to be a specifically fixed point. It is going to be an ever-changing foam of growing and shrinking, because at the same time that you have other stuff that does end up entering the system, you've also got its own rate of, you know, outward evaporation in some form or another. You know, Hawking radiation, in addition to whatever else we end up discovering out of it. But at this point, EA, no fight, don't play so rough. At this point here, you've got a foam area, a seaside, the actual, I mean, literally imagine if this was the shore, and here's the ocean, and here's the beach sand, there, beach sand, all right? This area is changing all the time. Water's coming in, water's coming out, water's coming in, water's coming out. Well, you got the basically, now take that to a 3-dimensional, 4-dimensional, however many dimensions we actually have that mass and energy move through. Now do that shoreline right around the black hole's event horizon, this outer shell. So you have light that gets trapped in there. And hypothetically, anyway, what would happen is this light would keep warping in and around and around and around this stuff, okay? And it would be, again, it would be very, very hard to tell what was going on at any particular point in time the more and more you zoom in. Now, if you zoom out past a certain point, you can see it doesn't really matter. The line blurs. It's all relative, you know. If you're larger than the black hole, or if you're another black hole or something to that effect, you're just not gonna care as much about that boundary. You know, if you're also the size of the thing and LIGO's about to pick the two of you up colliding together, you know, the actual boundary between these is a lot less precise before it matters. However, if you were, say, the size of a molecule, a water molecule or something, and you're approaching that little tiny spot in that horizon, you know, it zooms in more and more and more and more and more into the point where you can't even tell anymore what is and is not the foam, or the space between the bubbles in the foam, so to speak. So you have enough uncertainty, you have enough quantum uncertainty past a certain zoom in level, I guess you could say. So let's say that this area here, all right, let's say this area here, we've zoomed in now at the quantum level of where you have field interactions and the quarks, leptons, your ability to perceive what has happened in here is equal in size to whatever is happening in here, or greater. So what I mean to say by that is, if the very smallest thing that you can measure with is a photon, and the very smallest thing that you can figure out how to measure is another photon or an electron, you know, something like that, then, you know, you can launch it into there, but to get your response, it's got to bounce back out if you want to measure it. So you might, you know, boom, come in through this area, and you might randomly fly off that direction. But in so doing, you have now affected the trajectory of this, and maybe you send it inward or outward. You know, by the act, literally by the act of measuring the thing, you change its state, because otherwise you wouldn't be able to have observed it. And that tends to hold true for most things that we know of in physics at the, you know, quantum level and the level, unless things have changed recently, or unless my understanding just isn't that good. But as far as I'm led to understand, that would be the case. However, the other thing is, at the quantum level, light doesn't really appear to give a damn, because at the same time that this seems to be happening, you'll have you could have the same escaped electron that we talked about a minute ago coming out, and we know, okay, that electron that just came out also happens to be this same electron that has gone into the system over here. So you could have two separate systems, and you end up observing what appears to be the exact same electron going into one and coming out of the other, or some other oddball arrangement. So at this point in here, you wouldn't have, like, a black hole would not look black if you were to look at it. It would look like a glowy, it would look like a, I guess it would look like, well, it probably wouldn't look that different than any other star, just much, much larger would be my guess. Because you would have light that was trapped at this level. It would probably be doing way more incredible stuff the closer you zoomed in on it, and you could actually get details of the interactions of light going in and out and around it, and all the other bits au masse, and the bits and bobs and was names that make it so. But as far as your just run-of-the-mill planets and stars going in, things like that, you know, if you can average that kind of stuff out to the point where entire star systems are being considered a discrete unit going in, then again, the comparatively, relatively so, it just wouldn't look that much different. It would look like a just really big bright spot at the center of the galaxy. It would look like a greater and greater combination of stars. But the closer you were able to get in resolution as to what would have happened on it, you would see that all along its surface area, anything that had gone in, let's say, oh, you know what, let's make a new black hole, because that's always a good idea in science, right? We'll just use this black hole instead. So here we have another black hole that hasn't collided with that one yet. We'll use this black hole. Now, I was going to make a new point, about a new black hole. I sure was, and I think I've already forgotten it. I think. Oh, right. Anyway, the light. If you manage to get a close enough look at it, you know, what you would see is something probably not entirely unlike our sun, at least at the, you know, the distance resolution level. You would see photons in mass trying to escape, and then you would see them just as quickly getting pulled back down, or you know, at some kind of a rate of ejection and re-entry, or ejection and escape. It would just depend on what kind of a vector it entered the system at. Hypothetically, you could slingshot around a black hole the same way you could our sun or an asteroid or the planet Jupiter or anything that had sufficient mass and energy. But whatever photons that had not yet decided to eject and leap out of the thing, they're going to keep going in and out and in and out and in and out of the system, and then they're going to be sending out little spots. So in reality, the thing would be way brighter at the event horizon the closer that you got, because you would be able to observe more photons leaving the thing before they got pulled back into the system. You know, if you ever look at pictures of our sun, when it's ejecting coronal mass, you can see these beautiful waves of coronal mass ejection coming out, and then they curve back around into the sun again, because the sun has a whole lot of gravity to it. Well, you can just kind of picture the same exact thing with photons and black holes, right? So that is kind of what we've observed as far as black holes go, right? What happens when you induce that state artificially using a field propulsion engine, like the one I've mentioned before? Is so say you've got your field propulsion craft here, and it uses that. I'm going to make a very simplified field here. So, you know, you got your anode. I'm sorry, you got your cathode, you got your anode, you've got your inward, you know, thrust ratio, and then you have here where the, you know, the outer electric field is coming over here, propelling it from the rear, and it's going forward, right? But this shell, this outer shell, we'll just assume that the entire thing in the prior video where I had described how this system would work, this shell here would, while it's in place, any photons within that system, without particularly great resolution or whatnot, are going to kind of appear to do the same thing, I think, as a black hole would do. Maybe. Now, where it gets weird is that you're not actually generating gravity here. Again, as I mentioned, it's not like you're taking this natural force and that natural force and turning them off in the universe. That's really not how this is working, to the best of my knowledge. What's happening is you're using an electromagnetic effect to suck the air out from in front of the craft and use the same electromagnetic field current around it to push the craft from behind with the extra air as it comes in. But the field itself is going to be so powerful and so intense from the power supply that has to be used, because if you're using 25 million kilovolts or kilowatts or whatnot of electricity getting EA, don't play rough. Anyway, if you got all those, if you got that much going through it, you're gonna have an insane magnetic field going with it. But it's not necessarily gravity per se. It might just be somehow enticing the light from the magnetic field to crystallize to form visible waveforms, invisible waveforms. So within this area, it's not so much that you're trapping the light in an inward-outward thing like a black hole or a star does. Instead, what you're doing is you're taking all that light and you're basically saying, so you remember what I was saying about the electrons earlier, right? About how weird electrons are, where the electron that's entering this system might very well be the same exact electron that's exiting a separate system somewhere else. So that's one of the things we haven't quite figured out yet. That's why I really couldn't tell you, you know, unless I saw this thing up close and personal, what it could do. I could just tell you, you know, maybe what it might do. But if in fact it crystallizes in some representative form or another, the positions of each of these electrons or flow of them into a field, it basically freezes the light at that point. Because science. Hypothetically, the light would be just stuck at those points. It wouldn't be being emitted. It wouldn't be being sucked in. It would just be stuck there. It would be a, I don't know, like iron filings, I guess, except not. Maybe, I honestly don't know how the alignment of those would go. But yeah, it would affect the photons at a certain point. Now, what would it do with them? I honestly don't know. It might look completely dark. It might look invisible. It might look like a bright white, or might look gray. Might look like a rainbow, like in the Philadelphia Experiment movie. You know, I don't know. It's, if I were to hazard a guess, just from observation of other videos that I've seen, my guess is it creates a bright whitish field. That would kind of be the mixture of all the visible light spectrum, but it would probably appear in and out of different spectrums, just depending on the alignment of the direction of the field that you tell the electrons to be in, and as a result the photons will change. Now that's just a cool camo effect of it, but the other problem is, or opportunity in disguise, is that photons don't, when photons are in motion, they don't really experience time. I mean, so say you got a little photon leaving this star, heading for Starlandia over here. Whether it takes that thing 1 second or 100 billion years, as far as that photon is concerned, it was the same, you know, at one point it was born, and at the next moment it collided with something. There was no in between. As far as the photon is concerned, every little spot, every Zeno's paradox turtle arrow that you could fire at it along the way existed exactly the same for that photon, until such time as it was influenced by something. So if that is the case, and if you're actually freezing photons in place with this electromagnetic field, hypothetically, again, I think that's one of the things they were referring to in that .mil paper in the field propulsion area, when they said that all points within the field would be the same within space-time. And it may actually give a little bit more context to one of the famous conversations as well with I can't remember his name now, but the gentleman from Lockheed Martin, who, you know, smiled and said all points are the same in space-time. Well, I mean, that's kind of the reference point there. Anyway, it looks like I need to give up the chalkboard because I think my eldest is about to use it for basketball practice, and I've made enough of my point. Night watch, over now.